producers, all the way from phytoplankton and seagrass, all the way to top trophic levels like seabirds and fish. We can also look at changes in terms of the rates of change. So a lot of studies report how fast their organisms are moving towards the poles in terms of kilometres per decade. So this figure just shows the mean rates for different taxa, grouped by different taxa, and positive changes are poleward shifts and negative changes are equatorward shifts. I've just picked a few taxa here. So you can see that quite a few taxa on average are shifting towards the poles. There's some variability among taxa, so fish larvae on average aren't moving that fast, although there are some species that are moving very rapidly. And sharks on average were moving quite slowly, or perhaps even towards the equator. Could do the same for phenology. So a lot of studies report how many days earlier per decade spring events are occurring, and this is shown here on the y-axis with positive changes indicating days earlier and negative changes days later. So phytoplankton and zooplankton fish, all on average, showing phenological changes earlier in the year, which is consistent with warming. Seabirds were interesting because a large number of seabird species were moving earlier, but then there are also a large number of species that were actually moving their reproductive events later in the year. And those specific studies attribute this to mismatches in the timing of blooms. So if plankton blooms and seabirds' food sources are moving earlier in the year, but they're not timing their arrival at breeding sites with those blooms, it means they have to feed for longer before they have enough energy to breed. And so they might actually be moving reproductive success or reproductive events later in the year for seabirds. There's some interesting patterns and differences across trophic levels. I just thought, because this is the Fisheries Centre, I should look into the database and try and summarise what's been reported in terms of impacts to fisheries. There's not really enough in there to date to look at, I guess, a quantitative synthesis, but there's some interesting patterns. One of those is a number of studies report increasing temperature of the catch. And this is, just been reported on the global scale by William Chung and Daniel Pauly's work. But there were a number of smaller scale studies that have also recorded this pattern. So that's warmer water species increasing in prevalence in communities and colder water species decreasing in prevalence. Some other impacts of fisheries. Some tuna fisheries are having to change the timing of when they harvest because tuna migrations are occurring earlier with warming. But a big question mark still remains over how fishing and anthropogenic climate change are interacting to affect fisheries. I'll get to that a bit later. So there's evidence that climate change is changing fisheries, but is that having economic impacts to fisheries? There's a couple of examples of this in the database, which covers, I guess, what's observed. One of them is this size. So this copepod is an important food source for planktonic larval cod, and that's been moving north and decreasing in abundance in important cod fishery areas in the North Atlantic. And this has I guess it's estimated this is contributing to the decline in cod in that region, so potentially having economic impacts on the cod fishery. Another interesting case comes from the North Atlantic, where there's, in the southern North Sea, there's actually been increases in species richness as new species and warm water species have moved in from the south. But unfortunately, these are low value species. So while they're replacing other species which are moving north, they're not as valuable species. So this could also have an economic impact on the fishery. And I come from a conservation-orientated lab, so I just wanted to pull out a couple of examples of how climate change might be affecting marine conservation. Obviously, impacts to seabirds' reproductive success and causing them to breed later will potentially contribute to declines in seabirds, many of which are already threatened by fisheries bycatch and invasive predators on islands. And another really interesting case comes from where I grew up in Tasmania on the east coast of Australia, where the warming waters have led to the range expansion of this ecosystem engineering sea urchin, the little black spiky things pictured there. And that causes wide-scale kelp barrens. Those kelp beds are really important habitat for many, many species and also some key benthic fisheries. So that's already having a large impact on the east coast of Australia. So I guess undertaking this study of how climate change has already impacted the world's oceans led me to wonder, what can management do to address these impacts of climate change? And I want to put this question to you. Is effective fishery management or reductions of global greenhouse gas emissions more likely? So it seems to me that management on a local scale is more likely to be successful in the current climate of increasing emissions of greenhouse gases, and it's unlikely to stop. So I heard a recent report that we're pretty much locked into 2 degrees of warming now, and the infrastructure that's going into the ground in terms of oil drilling means that we're pretty much on a trajectory to 4 degrees warming. So there's likely to be really rapid climate change in the future. That's something that managers at a local scale are going to have to deal with. So one way that the ecology and science can inform what managers on a local scale should do is to try and understand how climate change is interacting with, I guess, local stresses that can be managed, like fisheries. Unfortunately, only 13% of our studies in our database, which represents what we know, what's been observed, what impacts have been observed, look at non-climate drivers of change. One really good study that did look at a non-climate driver of change was Seedale's study from California Coast. And they compared range shifts in exploited and unexploited fish species. And they found that the exploited fish species, with similar, by controlling for life history traits, exploited fish species were moving at a more rapid rate in response to warming than the unexploited fish species. And they hypothesised that this is because fishing causes range contractions, leaving a core population that's more susceptible to variations in the abiotic environment. We can ask similar questions with the database we compiled. So here I plotted the proportion of positive abundance changes as a function of the range edge. So if distributions are shifting towards the poles, then we expect that at the poles edge of a range, the abundance of a species will be increasing because that's moving, poles edge is becoming more suitable habitat for that species. Whereas at the equator's edge of the species range, we should be seeing abundance decreases as that range edge becomes less suitable for the species in terms of the temperature getting warmer. And so you can see in general, abundances are increasing at polar edges and decreasing at equator's edges. But I divided those up by species, fish species that are fished and those that aren't fished. And there's no significant difference, or at least there's no detectable difference. So this suggests that there's no effect of fishing on range shifts. However, it might be that the resolution of our database isn't adequate to detect it like Seedale did. So it really remains a big question about how climate and fishing will interact. So before I carried on with the next part of my talk, which is about managing the impacts of climate change, I wanted to make a brief comparison of fishery and conservation science. The lab I come from is really conservation focused, whereas I know here we're experts in fisheries management. So just briefly, fishery science has a really strong foundation in mathematics. This has been really useful for fishery science to inform management because they can make quantitative predictions about what you expect biomass to be and what catches you should be targeting, for instance. It also means that if I want to go and provide some advice, if a government agency asks me for advice on how to manage a particular fishery, then there's a large body of literature and some really well-established process models that I can draw on to provide that advice. Conservation science, on the other hand, has historically not been mathematical, although that's changing now. There's no one standard process model, so I can't just go and say, well, I'll use this age-structured stock assessment model to look at the problem. And there's numerous threats that have to be dealt with. So conservation science we're often faced with, as well as fishing as a threat, there's also pollution, coastal runoff, oil and gas developments, all those sorts of things. So this means the approach that we tend to take in Brisbane, that I tend to take, is to focus on trying to provide simple heuristics that can apply in many circumstances, and also approaches that can address multiple threats. So this brings me on to the second part of my talk, and this work was recently published in PLOS One. It's about how to managing for interactions between local and global stresses of ecosystems. So really addressing that question of how management at a local scale can deal with the impacts of climate change. So I guess the fundamental thing to consider for management at a local scale is how does the local scale threat, like fishing, interact with climate change? And there's a few views about interactions in the literature at the moment. The first one is that synergisms are prevalent. The synergism means that the combination of two threats, so say fishing and climate, together has a greater impact than you expect on their impacts alone. And this is really a concern because it means that things are going to get a lot worse in the future. So for instance, if fishing and climate change are increasing the mortality rates of a coral reef fish, then in the future we expect that mortality rate to increase exponentially, and things will get a lot worse for that species. So there's been a lot of focus around identifying synergisms. A second common view is that it's kind of that there aren't interactions, or that the different threats have cumulative impacts. And this is really popularised by Ben Halpern's work, where they did the global cumulative impact map. And I guess hidden in the mathematics of that map is that threats, you can just sum up the impacts of threats on a given ecosystem, and that's the overall impact. So that's assuming that there's no interaction, that the threats just have additive impacts on the ecosystem. And the third view is really about resilience. And that's that ecosystems such as coral reefs exhibit these phase shifts to alternate stable states, and that by reducing local pressures on that system, then, such as fishing, the system's less likely to shift to an undesirable state after a disturbance like coral bleaching, which is caused by climate change. The problem with all three of these views is that none of them really consider antagonisms. So an antagonistic interaction is one where the combination of two threats is less than you'd expect on the basis of those two threats alone. So an example, again, for coral reefs might be if you have a coral bleaching event which kills coral, and then destructive fishing practices which also destroy coral. Well, if the coral reef's already bleached and then you go and dynamite fish there, it's not really going to kill any more coral because the coral is already destroyed by the bleaching. So that would be an antagonistic interaction. There's been a couple of really important meta-analyses in the last few years, and they looked at the types of interactions across a large number of different experimental studies, and antagonistic interactions were just as common as synergistic interactions or no significant interaction. So antagonisms are out there and they're obviously important. The other problem with these views is that I argue they don't really tell us what to do and where. So they don't really inform managers about where they should take actions and which of those many threats they should be taking actions on. So to address these issues, I started with a couple of models, and I'll present both of those today. One's a population model, focusing on a community of seagrass bed, and another one's a community model focusing on a community of coral reef fish. So the first one's the